Okay, so section 7.4, here we go. This is a similar right triangle. So you'll see some theorems. Here, guys. Some theorems about overlapping right triangles. This one says the altitude to the hypotenuse of a right triangle, that's this piece right here, is the altitude to the hypotenuse of a right triangle, divides the triangle into two triangles that are similar to each other and similar to the original. Okay. So, well, you can see they each have a right angle here, and then in each case they share an angle. So by angle-angle similarity, you can make that statement. So I'm going to give you some a theorem and then a couple of corollaries. You can either use the corollaries to do the problems, to set up your proportion and solve. Corollary is a little mini theorem that comes out of a bigger theorem. So it's a little sub-theorem. It says here, what similarity statement can you write relating the three triangles in this diagram? So let's see if we can get the three triangles. They do share some angles here. At least let's see here. We have triangle QRP is similar to triangle. So we have QRP is similar to, can you name the correct corresponding pieces here of this smaller triangle that's similar to QRP?
No, C.
It would be.
Wait, S?
Okay, I started in the, okay, wait, in the big one I started with the hypotenuse. I went QRP, and so now QPS, yes, they share Q. And I want to go down the hypotenuse of this little guy. Let me outline here. So QPS is correct, which is similar to triangle. Okay, over here, I've got this triangle, and I want to talk about the piece that the big triangle and the red triangle share. So let's start with that piece. What angle do they share? No, they share R. So it's going to be R, and then go down the hypotenuse, so PS. So if you can take these overlapping triangles and separate them out, you can write proportions without ever knowing these corollaries. You don't have to memorize these corollaries to do it. Okay? So if you can do what we just did here,
So technically there's three triangles.
there's three triangles in one, and they are all similar, is what we're saying, because they share an angle. Like this Q is shared by the blue one, and then the overlap, the big one, and then they both have a right angle, obviously. But if you can separate them out in this way, you can write a proportion without ever memorizing these two new little corollaries I'm going to give you. Is that clear? So you can do this without memorizing them. But
what if you could just look at it and tell me?
You probably could. You could tell when they're distinctly different sizes. You probably can, based on how they're related, corresponding to the right angle. So, okay, so I'm going to get to the corollaries in a minute, but I have a definition here, and that is the definition of geometric mean. So for any two positive numbers, A and B, the geometric mean is the positive number x, such that A over x equals x over b. We call A and B are the extremes of the proportion. I think of it this way. The extremes are at the far ends, right? Zach, I asked you to move, and I expect you to stay in your seat. And it shouldn't be moving here. So Zach, right over here. Inside to move back. So A and B are the extremes. We call the x's, there's two of them, are the means. So it's always true that these two are the extremes that I just circled in red, and the means are always these two that I circled in green. And so keeping that in mind, it says, what is the geometric mean of 4 and 18? Well, there are two ways you could do it. You could set up a proportion and solve, or you could solve this proportion up here and get an equation to plug A and B into, or plug 4 and 18 into. So looking up here, if I cross multiply
X squared.
I get x squared for the means, and what are the extremes? AB. And how do I solve this equation, x squared equals AB for x? Find the square root of AB. So another way to define the geometric mean is it is the square root of the two numbers, of the product of the two numbers, sorry. You multiply the two numbers and then take the square root. So the geometric mean is the square root of the product of these two numbers, where 4 is A and 18 is B. We multiply them and find the square root. So the geometric mean will be 4 times 18, and then take the square root. And if the square root is not a perfect square, like this one is not, we just leave it in that form. Square root of 72. Next chapter we'll talk about simplifying. I'm going to review simplifying radical expressions with you. But at this point, if you could just leave it, square root of 72. Now, let me give you a little bit more information about geometric means here. Let's try one more. The geometric mean between 4 and 16. Okay, now don't get confused. When we say geometric mean, that's different than what we call the arithmetic mean. The arithmetic mean is what you've learned as the average. Yeah. When I say what is the arithmetic mean, or if I just said mean, you would assume arithmetic mean between 90 and 100. Like Tanner got a 90% and 100% on his two tests. So the arithmetic mean would be 95, halfway in between. So an arithmetic mean, 90 to 95 to 100, they all have a difference of 5. A geometric mean has a common multiple or ratio. Okay, that's how it connects to what we're talking about now, is they are separated by a common ratio. So the geometric mean of these two numbers would be the square root of 4 times 16. Well, 4 times 16 is 64, so the square root of 64 is 8. So what I'm saying is the geometric mean between 4 and 16 is 8. Well, it's not the middle in terms of like a midpoint, like we know that's the arithmetic mean, but it is a middle in a sense, because to go from 4 to 8 we multiply by 2, and to go from 8 to 16 we multiply by 2. This is called in algebra 2 you'll learn it's called a geometric sequence. And a geometric sequence is a list of numbers, and you get from one number to the next by multiplying rather than adding. That's it. Those are two very important sequences in algebra 2 that you'll study: geometric sequences and arithmetic sequences. So what would the next number in this sequence be? 32. 32. And what would the geometric mean between 8 and 32 be? 16, yeah. You would multiply these two and take the square root, and you would get 16. Okay. And what's the next number after 32? Okay. So that's an example of a geometric sequence. You'll study those part second semester next year.
Are we going to get to a point where it gives us two numbers, but then it asks us to find, like let's say it gave us 4 and 16, and it asked us to find between 16 and 64. I mean, that'd be kind of a waste, but you could always just find 4 and 16 and 8 and just keep going up.
You could. I'm just going to ask you, what's the geometric mean between two numbers? I'll give you the two numbers, and you just need to multiply them and take the square root. The geometric mean, it all kind of relates to proportions and ratios here. If you remember, the means are these two. And these are the extremes, but if you solve this equation for x, you have your formula for the geometric mean. So we're going to use that language that we just learned in here. You have it all written out there. So let me try to match these shapes up. It says the length of the altitude to the hypotenuse of a right triangle, and they're talking about the big right triangle here. So we're talking about this. The length of that red piece right there is the geometric mean. So we're going to put the 4 in the means place in the proportion. Is the geometric mean of the lengths of the segments of the hypotenuse. The segments of the hypotenuse are the two pieces that the altitude splits the hypotenuse into. So this piece right here goes in the mean spot, and these two values go here and here. That's it. So it's just setting up a proportion. And okay, remember, you could always separate out the triangles and just write a proportion to solve for the missing side length, right? But this corollary will take a picture like this in example 3 and allow us to solve for y pretty easily without ever separating out the triangles. What does y match up with in this picture? What does y correspond to in this picture? The 4. So the y is going to go in the spot where the means go, right? And what do the 4 and 5 correspond to in this picture up here? The 2 and the 8. So the 4 goes here and the 5 goes here. And so I can find the length of y without ever separating out the similar triangles.
So the means always have the one in the middle of the bigger.
It is, yes. It's the, well, middle, it's the altitude to the hypotenuse. And so that will be the mean, and the two pieces that the altitude splits the hypotenuse into will be the extremes. So it's y squared equals 20, so y equals square root of 20. So the length of that piece is the square root of 20. And so there'll be pictures that look like that. It's just a matter of matching them up. If I want you to use this corollary, I will give this corollary to you. You know, if there's another way to do it, then you can do it that way, or separate them out and write a proportion that way. The second one says the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. That's a mouthful. You have to look at the picture here. What it's saying is that if you draw the altitude in the big triangle, draw the altitude over to the hypotenuse, this little piece right here, okay, that is adjacent to the hypotenuse, this little piece right here that's adjacent, will become the mean, and then the extremes are the whole length of the hypotenuse over the little leg that's adjacent to that piece. So it looks like this. You kind of have to just match up the pictures. What corresponds to the 2 in this picture? It's the x, yeah. So we have the x going here and here. And then what corresponds to the hypotenuse here, the 4, in this picture? It's the 9, yeah, it's the 9 actually. The 5 is just the little piece here, and the 5 would actually go with this over here, which is not even used in this formula. So the 4 would go down here. You know, the other way to do this is just to separate these out. We have 9 is to x in the big triangle, right? 9 is to x. This goes back to example 1. 9 is to x in the big triangle as x is to 4 in this little triangle on the left. I mean, you could separate them out and just write a proportion in that way, and you'd be fine. So x squared equals 36. What does x equal?
6.
6. I have a little link on here, but it logged me out, so I can't use the link. I discovered you can only use a link if you're logged into the textbook, because it's a link to this same problem in your textbook. It's in color. But what's happening here is you're preparing for a robotics competition. Here's your little robot over here. Your robot is going to come over and pick up this piece of trash and then take it and get rid of it. So it says points A, B, and C are located so that AB equals 20. AB is perpendicular to BC. You can see the right angle here. AB hits BC at a right angle. Point D is located on AC so that it's perpendicular to this base down here. And that DC is 9 inches. So you program the robot to move from A to D and pick up the plastic bottle at D. How far does the robot travel from A to D? So we have to solve for x here. And we're going to obviously use one of these corollaries. Can you tell which one? First or the second one? You can tell. It is the second one. To use the first one, you would have to have the length of this piece if you match them up. So either a good hunch there. So the 20 goes with what in this picture for the second corollary? The 2. So the 20 will go here and here. at the means positions. And then we have up here, the hypotenuse is this whole piece, which is 9 plus x, and that goes right here. And then the other piece, this 1, corresponds to this little piece right here, well, littler piece, which is adjacent to the 20, or the x. So what this does is just like in problem 24 from your homework that you asked me about, is it creates a quadratic equation. So I cross multiply, I have 400 equals x times 9 plus x. I'm just going to write it down here because I don't know if everybody's seeing this here. So x times 29 plus x. So I have 400 equals 9x plus x squared. One more step before I solve by either factoring or the quadratic. Just subtract the 400 over, right? So 0 equals x squared plus 9x minus 400. So the question is, can this, move it up a little bit, can this be factored? Are there factors of negative 400 that add to equal 9? Anybody think of them right off the top of their head? It doesn't work. Can it be factored? If it can't be factored, we would have to use the quadratic formula. Some might argue it's easier to go straight to the quadratic formula in this one. I think I would argue that. Because if I start thinking of factors of 400, here I have, 401, and then I have 202, and then does 3 go into 400? No. 4, yeah. So 4 and 100. You see what's happening here? I got to get way closer together before I ever find factors. Is it factorable? It may be. But it might be easier just to use the quadratic formula than it would be to factor. Unless somebody thought of factors yet? Do you have them yet?
26.
You think you have it?
Is it 25 and 16?
25 and 16?
Oh, wait. One of those.
I think that's it. He's got it. So working together, we would eventually get 20. So you're saying 25 and 16?
Yeah, one of those would have to be negative.
Negative, yeah. And he is right. Well, guys, let me finish up here. So I have 0 equals x minus 16 times x plus 25. And so my solutions are either x minus 16 equals 0 or x plus 25 equals 0. So x equals 16 or x equals negative 25. Which one makes sense for this problem? The 16, we'll toss that out. So how far does the robot travel from A to D? 16 feet. And that's using corollary number 2.
Hey, where's my
Oh, quadratic formula would be x equals negative b plus or minus square root b squared minus 4ac all over 2a. You can use that in today's
with the giant conspiracy.